Would you like to learn a simple method to synthesize graphene? Let me show you. Graphene is a two-dimensional material composed of a single atomic layer of carbon atoms arranged in a hexagonal, honeycomb-like lattice. Each carbon atom in graphene is sp2 hybridized, meaning it forms three strong covalent sigma bonds with three neighboring carbon atoms. These strong sigma bonds create a highly stable and rigid in-plane structure. The remaining unhybridized p orbital on each carbon atom overlaps with neighboring p orbitals to form a delocalized pi electron system that extends across the entire graphene sheet. This delocalized pi electron cloud allows electrons to move freely within the graphene plane and is a key reason for graphene's very high electrical conductivity. In nature, graphene does not usually exist as an isolated layer. Instead, multiple graphene sheets stack together to form graphite. Within each graphene layer, the carbon-carbon bonds are very strong. However, between adjacent graphene layers, the interaction is governed by weak van der Waals forces. These weak interlayer forces are much weaker than the covalent bonds within the graphene plane. As a result, the stacked layers in graphite can be separated by supplying external energy. This separation process is known as exfoliation, in which individual graphene layers are peeled away from bulk graphite. Importantly, exfoliation breaks only the weak interlayer interactions, while the strong sp2 bonded carbon network within each graphene sheet remains intact. Now let's look at the electrochemical setup. We use a graphite electrode as anode, a counterelectrode, an electrolyte, and a DC power supply. When a voltage is applied, ions from the electrolyte start moving under the electric field and interact with the graphite layers. This setup is easy to implement, making it ideal for the easy synthesis of graphene. The exfoliation process happens in three key stages. First stage is intercalation. Under applied voltage, ions and solvent molecules insert between the graphite layers. This increases the interlayer spacing and weakens the van der Waals forces holding the layers together. Second stage is expansion. As intercalation continues, gas evolution and electrochemical reactions cause layer expansion. You can actually see the graphite swelling and breaking apart. Third stage is exfoliation. Finally, the expanded layers separate into few-layer or single-layer graphene sheets, dispersed in the solution. This electrochemical approach is important because it offers several key advantages. It uses a simple experimental setup, making it easy to perform even in a basic laboratory. The synthesis is fast, allowing graphene to be produced in a short time. The process is scalable, which means it can be extended from lab scale to larger scale production. Most importantly, it causes minimal structural damage to the graphene layers. There is no need for harsh conditions, such as high temperatures or strong oxidizing chemicals. As a result, high-quality graphene can be synthesized efficiently and reliably. Thank you for watching. Subscribe for more videos.